In a previous video, we've looked at what parametric equations are. They are functions in terms of a given parameter. Usually we use that parameter of t, so we express x as a function of t and y as a function of t. But now, of course, we're in a calculus class and we want to find the slope of a tangent line at a given point. So first of all, let's for a minute say that we've eliminated the parameter and we can rewrite this function in terms of x. So now we just need to find the derivative. Well, before we do that, let's kind of make some substitutions. So right here, in place of y, we could put g of t, and then in place of x, we can put f of t. So we have a function of t. And I know that looks weird, but just give me a minute. Now we want to find the derivative. Okay, well that should be fairly easy. So we take the derivative of g with respect to t, because that's your variable. But how would I find the derivative here? Well, we're going to have to use the chain rule. Remember, if you have something like y equals 3x plus 1 squared, we would take the derivative of the big function, multiplying it by the derivative of the inside function. Well, that's what we're going to do here. We're going to take the derivative of big F and leave the inside alone, multiplied by the derivative of that inside part, if you will. Remember, that's just the chain rule. Okay, so that looks kind of really ugly. Let's see. What was f of t? Wasn't that x? So we have the derivative of g with respect to t. We have our capital F. Now remember, our capital F is a function of x. In fact, so we have the derivative of our function of x, because we're going to now replace, go back, what is f of t? It was x, multiplied by the derivative of lowercase f, and that's our derivative with respect to t. Man, that's really ugly. Let's see if we can do some rearranging. Can I not divide both sides by f prime of t? I think I can. I think that is allowed. And so, just going to write it backwards, if you will, and say, okay, our derivative of our function with respect to x is our derivative of g with respect to t and little f with respect to t. Well, back up here. Again, what was g? That was y. What was f? That was x. So really, what this is g prime of t, or the derivative of g with respect to t, is dy dt. This is the derivative of x with respect to t. Remember that y was a function of x, that we use capital F. So now we can replace this notation with dy dx equals dy dt over dx dt. And of course we have to say that the derivative of x with respect to t cannot equal to 0, because we don't want to divide by 0. But that is your first derivative of the parametric equation. Easy enough. In fact, if you look, it just says take the derivative of y with respect to t, take the derivative of x with respect to t, and divide those. And that's your first derivative. But what about the second derivative? Well, we're going to do a little algebra. we're going to take the derivative of the derivative. That's what we learned in Calculus 1, so it should still be true in Calculus 2. So I'm going to say, well, let's take the derivative with respect to x of both sides of this first derivative. So we have the derivative with respect to x of our first derivative. Well, that doesn't look too bad, but remember our second derivative is with respect to x, but x is a function of t. A little confusing, but we're going to get there. So let's see if you remember how to write that. Remember the second derivative we learned in Cal 1 can be written like that. Right? Over here on the other side, well, what can I do algebraically? I can do just a little bit of rearranging. So I'm going to take these dt's and bring them outside the bracket and rewrite it like this. So I have d dt divided by dx dt, and what that leaves me inside would be dy dx. Now that's convenient because dy dx is our first derivative, and it's nice to be able to take the second derivative based on your first derivative. So I'm just going to rewrite that a little bit differently. So I have d dt. What does that mean? I'm taking the derivative with respect to t of dy dx, which is our first derivative, divided by dx dt. That is our second derivative. So look closely, what do we have? We have the derivative with respect to t of our first derivative divided by the derivative of x with respect to t.